Hello, I'm Yoav Baumgarten. I'm taking the opportunity to present this joint effort with Mark Psyche and David Hazel. In this work, we show that a network of ground-based, high-frequency beacons has the potential to provide useful measurements that can be used to determine the location of a user receiver. HF signals propagate along ray paths that may include multiple reflections from the Earth and the ionosphere. The exact signal trajectories and propagation speeds depend on electron density in the vicinity of the propagating signals. This electron density distribution is typically unknown and therefore poses a challenge in the localization process. A spatial electron density model is used to determine electron density near the propagating signals. It is based on a three-parameter Chapman vertical profile where biquintic surfaces are used to represent the three parameters dependency on location. A method has been developed that determines the exact path for propagating signals, including the location of reflection points where signals are reflected from the Earth. This method utilizes ray tracing computations. Measurement models for group delay and range equivalent bit carrier phase measurements have been developed. Both types of observables are sensitive to variations in the location of the receiver, as well as to variations in the ionospheric model. This constitutes the coupled localization and ionosphere characterization problem. The problem is solved with a batch filter that minimizes differences between measured and predicted group delay and range equivalent phase measurements. Optimization is simultaneously performed for the unknown location of the receiver, its clock bias, and several hundreds of parameters that characterize the ionosphere in a region that includes the receiver and the transmitters. A simulation has been developed that enables the study of different test cases. In test case E0, 32 different signals are received at the receiver whose location is unknown. The transmitters roughly surround the receiver so that signals arrive to the receiver from a variety of directions. The true ionosphere model is slightly different from the a priori model that is used with the filter. Resulting accuracy for this test case is demonstrated in the left plot in terms of a 90% error ellipse. The horizontal error is in the order of tens of meters, and the average error is only slightly biased. The horizontal error ellipse takes a very different shape for test case D2 on the right. More about this in the paper. For test cases of a constant a priori ionospheric model, significant errors in the a priori model are typically reduced to very small errors for their a posteriori counterparts, as demonstrated here. It has been shown that with a sufficient availability of observables, positioning errors are in the order of tens of meters, even with a random a priori ionosphere model that represents poor knowledge of the true ionosphere. Thank you, and I hope you enjoy the paper.